Welcome back to Principles of Electronics. This is lesson number 12. Today we're going to be talking about series and parallel circuits. We're going to start by defining how voltage, current, and resistance relates to each one of these, parallel and series. And then in the end we're going to do an example of each one with given values. All right, so let's start with series. Series always seems to be the easiest. Series circuit, as you can see, just visually, it is one loop. Now, if you have an additional loop out here, that's a whole different game. That's called a complex circuit. But with a series circuit, you have one loop. In this example, or in this diagram or schematic, I have three different resistors. Those resistors really represent a load. So this could be a buzzer, this could be a fan, this could be a light, whatever. All of those things, all those have resistances. So we represent those just with simple resistors. And it makes it easier for calculations and so forth. So let's look at some relationships. Now, first thing that you have to understand is when voltage here goes through a resistor, it drops. So you get a value here and a different value here. And the difference between those two values is the voltage drop. Then this value goes into this resistor and it drops and you get a different value out here. And the same thing for this last resistor, to where in the end you end up with 0 volts. So your last drop is whatever this value is down to 0. And that's the case for parallel over here too. You get a drop, but that looks a little bit different. So given that, we know then that our voltage, our total voltage, which is really our battery voltage, is the voltage drop across R1 plus the voltage drop across R2 plus the voltage drop across R3. And this should make sense. If you're dropping whatever voltage you have here across each resistor and you drop, you end up with 0, it should equal the total, each drop. Current is a little bit different. Current, your total current in a series circuit never changes. So whatever current, total current you have, whatever current you're drawing, is the same current through each one of these loads. So the current in R1, is equal to the current in R2, and that's equal to the current in R3. That's an equal sign. Now, resistance. Resistance, if we were to measure the resistance with a meter, if we had a meter and we measured from this point to this point and we took the battery out, we would get a total resistance measurement. We could measure each resistor if we wanted to. But for our total resistance that we would measure, and this is important down the road for different circuits, is very similar to the voltage. It's R1 plus R2 plus R3. Notice V equals IR. We're still talking Ohm's law. We're still relating Ohm's law to, in this case, a series circuit. Now let's go over and do the same thing and see what our relationships and our equalities are for a parallel circuit. I still have my total voltage here, which is my battery voltage. But this time, each one of my loads is in parallel. And again, these could be different things, lights, fans, buzzers, whatever. But they're in parallel. And hopefully visually you can see the difference between these two. The difference here, though, is now our total voltage drops across each resistor. So for example, if this is a 9-volt battery, I have 9 volts here, 9 volts here, 9 volts here. It's got 9 volts in this entire node. This node obviously has to be 0 because it goes back to the negative of the battery. So if it's 9 here and 0 here, I'm dropping 9 volts across each one of those resistors. So I'm dropping the same amount of my battery. So VT is going to equal VR1, and that's going to equal VR2, and that's going to equal VR3. If I had 100 resistors here, it'd be the same. Wouldn't be any different. Now, my current, though, is different. Current, when it comes to a node, splits. So if I have current coming out here, some current goes this way, some current goes this way. And then when I get to this node, some current goes this way, some current goes this way. And it's not the same. It splits. So I can then say my total current, which is right here, is equal to IR1 plus IR2 plus, that's 2, plus IR3. So if I add up the current across each one of these resistors, then that will equal the total current that this circuit is drawing. And hopefully that makes sense. Now remember, we're not dropping current like we are voltage over here or here. What we're doing is the current is splitting when it comes to a node. Some has to go this way, some has to go that way. Remember all that electron flow? Well, some electron flow is going this way, some electron flow is going this way. Now, what determines what that electron flow is and the value of the current is, of course, our resistor, and we go back to Ohm's law. Now, resistance is a little bit different. Resistance, there's a couple different things we can do. So if our resistances are all the same, let's say we have 5 resistors and they're all 10 ohms, then our total resistance, again, where we measure here and here without the battery, is equal to the value of the resistor divided by the number of resistors that we have. That's the easiest equation. The value of the resistor divided by the number. So if we had 3 10 ohm resistors, 3 10 ohm resistors, so it would be 10 divided by 3. That would be our total resistance. Now, if we only have 2 resistors, then our total resistance is equal to R1 times R2 divided by R1 plus R2. So that's not too bad of an equation. Now I will say, and this is a rule of thumb, that in a parallel circuit, only in a parallel circuit, your RT is going to be less than your smallest resistor. So like we had here, 10, 10, and 10, we use this equation. 10 divided by 3 is about 3.3. That's less than 10. If we had 2 10s and we did this equation, we get 10 times 10, 100 divided by 20. 100 divided by 20 is less than 10. So it's a rule of thumb in a parallel circuit that your total resistance will be less than your smallest resistor value. That's important to remember. Now, the one equation that we always want to try to avoid by using the top two is if we have more than 2 resistors and they are different, we have to use this monstrosity. And again, this will give you the same value. This will give you a total resistance that's less than the smallest value. So once again, what do we have? We have an equation for volts, an equation for current, an equation for resistance, which, we have 3 for resistance actually, which takes us right back to Ohm's law. All right, so let's do an example. So let's say over here we have a 10 volt battery, and we have some resistances here. Let's say we have 2 ohms here, we have 3 ohms here, and we have 5 ohms here. And I'm just really going to use easy numbers. So I can find every value that I need using these equations. So for example, if I have 3 resistances, I can find RT. So my total RT is just 2 plus 3 plus 5, which that's going to give me 10 ohms. Okay, that's good. Now I can use Ohm's law because I know that VT is equal to IT times RT. I know VT, I know RT. IT then is equal to VT divided by RT. So that's going to be 10 divided by 10. That's going to give me 1 amp. So I know that my current going across each one of these is 1 amp. Well, I can also use Ohm's law. Since I know what my resistance is and I know what my current is, I can figure out the voltage drop across each one of those resistors. So for instance, the voltage drop across R1 is going to equal the current on R1 times the resistance of R1. And that's going to equal 1 times 2, which gives me 2 volts. Again, I told you I made the numbers easy on this one. So this is 2 volts. I'm dropping 2 volts here. And you can see if you keep going, that's going to be 3 volts, that's going to be 5 volts. You add those up, you end up with your total voltage, which satisfies this equation. Okay, so that's a series circuit. Now let's go look at a parallel circuit. Let me get rid of this here just a little bit so I can have some room. Again, a parallel circuit is a little bit different in that it may be a little bit more harder to solve based on what you have for resistors. So let's use, I don't know, let's just use the same values. Or, no, let me use some different values here. I'm going to try to make this a little bit, the numbers a little bit easier. But let's say I already gave you an example with if they're all the same and if they're not. So let's say they're all different. So this could get, this could get a little dicey. But let's go, let's say we have a 10 volt battery. Let's say we'll just go again with a 2 ohm and 3 ohm, and then let's go with a 5 ohm. No, let's go with yeah, let's go with that. So I may not do the math all entirely, but I'm just putting values in as we go along. So first thing we need to figure out here is our total resistance. Once we find our total resistance, we can find our total current, and then we can get our current across each one and our voltage drops and so forth. But we actually do know our voltage drops already because since we have 10 volts here, we have 10 volts across this resistor, 10 volts across this resistor, and 10 volts across this resistor. So we may get lucky here and not have to use this to find RT. Remember, the goal here is to find every single thing there is to know, voltage, current, and resistance, about each one of these loads, in this case resistances. So if I know that my voltage drop from here to here is 10 volts, and I know that my resistance is 2 ohms, then I can just go, all right, well, my VR1 is equal to, my IR1 is equal to my VR1 divided by my R1, and that is 10 divided by 2, so that equals 5 amps. Then I can say the current across R2 is going to be VR2, which is 10 divided by 3, so I'm looking at about 3.3 ohms. I'm sorry, 3.3 amps. And then again, my current across R3 is 10 divided by 5 ohms, which is 2 amps. So I know the current, 5 amps through this load, 3.3 through that load, and 2 amps through that load. And I know that my equation for my total current is all of those added together. So it's 5 plus 3.3 plus 2. And that's going to give me 10.3 amps. So that's what I would be pulling out of this particular battery here to supply those three loads is 10.3 amps. Now, I could use this equation and I could put those resistances in, or I could just say my total resistance is my total voltage divided by my total current. That was my total current, which is equal to 10 divided by 10.3, which is, obviously a little bit less than 1. I'm just going to say a little bit less than 1 ohm. And obviously we can do a check on this. Less than 1 ohm is less than our lowest value of resistance, and so we know we're probably in the ballpark. All right, so let's recap real quick. Series and parallel circuits. Independently, a series circuit is a loop, and a parallel circuit is just what it says. It's all your loads are in parallel. We've defined how voltage, current, and resistance relate to each one, and we've given an example for each one using numbers that really aren't true life numbers, but they were easy numbers to get the idea of how the current and the voltage and the resistance work in these two circuits. All right, if you have any questions, please leave them in the comments, and as always, please subscribe to SpriderWeb Education.